Okay, day two, we talked about, or rather, you did labs about volume. Um, each day we do a different property of matter, for the most part, volume, and then day three is going to be mass, and then so forth. So you're kind of building up. That's essentially what this class is. We do mass, we'll do volume, and then surprise, surprise, we'll do density. But volume was day two. Volume is basically a quantification about how much space an object occupies. To have volume, you generally are going to need to be three dimensions. Okay, you have to be three dimensions, to be honest. So you got to have length, width, and heights. Haven't seen this in a long time, but maybe I should change it since I haven't seen it in so long. But units are centimeters cubed. You can say cc's. I prefer centimeters cubed over cc's, just because it if you need to convert units from one to another, cc's is kind of it's a little bit misleading. If you need to convert, like, say, cubic centimeters to, say, cubic feet, the cubic centimeters will actually make it better, the centimeters cubed. So that's kind of what I prefer. Also, milliliters, if you're measuring a liquid, also makes sense. You can't do milliliters cubed. That's the one thing I said that I haven't seen in a long time. But yeah, if you have cubic milliliters, then you have 9-dimensional object, which not sure what that looks like. Sure, it's pretty cool. Capacity. In the lab, we concern ourselves with the actual volume of the object and not its actual capacity. The volume is how much space the object displaces, and the capacity is how much volume, say, a container could hold. So this is Oracle's super fast, speedy sailboat that they built for a sailing race. The volume would be like, let's say we take this whole thing, dunk it underwater, find out how much the water level raises, and as long as we're in some sort of massive graduated cylinder, we could find out the volume. The capacity is more concerned about how much weight and how many people we can throw on top of this sailboat. I put a picture of this sailboat because it's particularly awesome. It's a sailboat, and it normally, when it's just without moving, it'll be sitting at the very bottom right here where my cursor is. But as it gets faster, it's designed to pull up and rest on these little skis, which then lowers the friction with the water. And as a result, this sailboat, based off the wind, can get up to speeds of 90, or not 90, sorry, that would be really good, but still 55 miles an hour for a sailboat, which I think is just crazy that you can go 55 in a sailboat. But yet it can. It costs, like, I don't know, I'm just going to make up a number because it was in this area of like hundreds of millions of dollars. It really did. So it's pretty expensive to go 55 miles an hour in a sailboat, but still kind of cool. Well, methods for determining volume in a lab. We can use math, height times length times width, or 4/3 pi r cubed for a sphere, 1/3 pi r cubed for a cone. You can use the Centicube model. The Centicube model is actually kind of interesting because if you try to, say, take the volume under, right, the area under a curve, for, like, computing, you kind of, in a weird way, use the Centicube model, which is kind of cool. But clay model, you can make an object of the clay and then measure it that way. But water displacement, obviously, most people know about and is the most common. Well, how do you do irregular objects? Well, that's why we use different methods. You can use the clay method for irregular objects. You can use a Centicube to approximate it, but even the clay model itself is also approximating. You could try using math, but even with math, you are still generally approximating. For instance, in my graduate research, I had to do a ellipsoid, which is like an egg-shaped object, and there's no formula for that. It's only an approximation, and I had to dig into a bunch of math journals to figure out what equation to use so I could figure out how many neutrinos are going to escape my detector. But the point is, on the larger scale, a lot of things are still approximated. So all those computer models, they're approximated, but it's a good approximation at that. Water displacement, why do we use it? It's pretty accurate. Crows can do it. That's why I picture a crow there. It's fairly direct, meaning anybody could pretty much use the water displacement method and more or less get the same numbers. If you compared your clay model groups between person to person, you probably got very different numbers, maybe even the same with Centicubes, because there's a lot of variation there and people are going to do things differently. But with water displacement, you're pretty much all going to read the exact same number, unless you can't read a graduated cylinder. That's another problem. It works for the large number of objects, which I apparently decided to put twice, and I need to fix that. That's another thing I need to fix. Oh, I didn't notice that. And it can work for any sized object as long as you got a graduated cylinder big enough. Essentials of water displacement. Basically, you could kind of an operational definition. The container is filled with liquid water. The container must have some type of markings on it to indicate the values of the volume. So you can use like a plain glass cup, but you can't really measure volume with it because you don't have markings on it. Can you make a plain glass cup into a graduated cylinder? Sure you can. It's kind of what beakers are. And in this class, we define liquid to be a matter with a definite volume that takes the shape of its container. A liquid, like air, is a fluid, but a liquid is a little bit different in that it's not gaseous, and that it will take the shape of the container just like a gas does, but it is under the influence of gravity when it takes the shape of the container. That's what a liquid is. And some gases are like that too. I think, chlorine is pretty heavy and stays towards the bottom and kind of acts like a liquid in a weird way. Essentials of water displacement. When measuring volume of an object, you should make sure the object is completely submerged, clearly. Make sure that all the air that is not intrinsic to the object is expelled. And the two examples are kind of like a glass jar and a basketball. A basketball doesn't really function if it doesn't have air into it, so that air is intrinsic. A car tire, generally that air is going to be intrinsic to the object. But let's say you want to find the volume of a tissue box that is completely hermetically sealed. Well, you're probably going to want to find the actual volume of the tissue box itself, but not the air inside it. Or a glass jar. I said tissue box because I'm staring at one right now. I guess I probably should use the glass jar since I put it in there. But you get the picture. And that's it for day 2. Like I said, a lot of these lectures are pretty short. The first few chapters, your first whole section is actually pretty, I wouldn't say simple necessarily. I mean, it is simple, but it's not as demanding as your second section when we do kinematics and your third section when we do thermodynamics. But more on that later, and I will see you guys on Monday.